So our topic for today is all about control systems and feedback. So when we say control system, it consists of subsystems or processes assembled for the purpose of controlling the output. So controlling the output is our main purpose. Okay, so ideally this is what a control system looks like. So we have the input and then the control system. This is where the processing happens, and then we have the output. So if our input or our desired response is 5 volts, ideally without losses, our output should actually be 5 volts as well. Okay, the output is our actual response. So our goal here in control system is to match the output to our desired response, which is the input. Okay. Now this is our system response characteristics. As you can see, we have here a delay. This is what we call the transient response. This is the response at the switching on of our system, right? That's the delay. And then slowly it will reach its steady response, and that is what we call the steady state response. Now, this straight line here is our desired response. As you can see, there is a slight gap. This gap is what we call the steady state error, which is the lesser, the better. Okay? So the steady state response is the actual response or the output of the system. So this is just like the graphical, um, this is just like the visual representation of the non-ideal characteristic of this control system. As you can see, the desired response is not the same with the actual response. There is a small gap or error between them. Now, we have two types of system configuration, namely the open loop system and then the closed loop system. When we say open loop system, the control action is independent of the output, meaning once the actual response was created, it will never be fed back to the input. Okay? It is independent of the output. While when we say closed loop system, the output is measured continuously and is fed back to the input. So we have a feedback. As you can see, in the open loop system, it is linear, right? Input, control, and then the processing, and then the output. It is linear. While in the closed loop system, as you can see, we have the input, and then the controller, and then the processing. And then as you can see, we have here an arrow that goes back to our error detection. Okay, so for example, our desired output is 5 volts. And then once it was processed and then it came out as 4.5 volts, then this one will be fed back to this. And then this error detection, this will measure the voltage continuously in order to match the input. So it will adjust continuously. So from 4.5 volts, it will adjust to 4.51. Then it will be processed and then be fed back here. Then assume, let's say it became 5.52, then fed back again because it still did not match the input of 5 volts, right? But you should remember that no matter how the output or the actual response will be fed back to this error detection, it will never reach up to 5 volts because in real life there were losses, right? 100% efficiency can never be achieved in real life. Okay, next we must review the Laplace transform because it is extremely important in learning the control systems. When we say Laplace transform, it is the tool that represents the frequency domain of the time domain function. Okay, so from frequency domain, it will be converted to time domain. Now the question is, in control systems, why do we have to convert? That is because it is essentially too complex for us to analyze complex waveforms. And in order to less complicate the analyzation of complex waveforms, we convert them to time domain functions. Okay, so this is an integral transform, and then the comparison of an integral transform to a Laplace transform. As you can see, so this is our Laplace transform. It is closely similar to integral transform. It was just converted. Okay, as you can see, both of them has an output, then they also have an input, and then an integral kernel. Right? They're just essentially equal, but the other one is converted to the other. Okay, so I will be discussing the examples number 1 and the properties of the Laplace transform in our next video.